Hello everybody, and welcome back. So in this next lesson, we're going to be talking about vectors, and particularly how we can start using them or manipulating them mathematically to achieve the results that we want in 3D. So in order to start working with vectors, we need to understand what a vector really is. So I've prepared a little example here just to talk about the true sort of meaning of a vector and how we can work with them. So this is just a very simple example. We have a cube here. There's 8 points in this cube. And here the green line is representing essentially just the point position relative to the origin. So I'm going to switch on the grid here and we're going to have a look. Now, theoretically, what a vector is just any number or multiple numbers that result in a vector, which is basically like an arrow, okay? And that this arrow represents two things. It represents direction and it represents magnitude. In other words, how long is this vector, but also which direction is it facing? Now, obviously we're working in 3D. We come across 3D vectors all the time. So point position, normals, velocity, that's all 3D vectors. But some others you may come across a lot is color, for example, RGB. Those are vectors, but they just are not really represented in terms of, a vector as we would imagine them, like this, an arrow. And yet their magnitude does matter because their magnitude is essentially their luminance. So how bright the color is determined by the sort of the sum of all the components in it. We also have four-dimensional vectors like RGBA, if we include alpha in there. Or, we have quaternions. Those are four-dimensional vectors, which we'll talk about a little later in this course. We also have two-dimensional vectors. In the last lesson, we were looking at sort of grids on X and Y, curves with just X and Y, but no Z. Now, those are two-dimensional, okay? And obviously, even just a normal kind of maybe Photoshop document or something, you've got a grid of pixels. That's a sort of X and Y flat two-dimensional object, and it has vectors, okay? And it's also good to understand that even normal numbers are vectors, really, sort of theoretically, because although they don't have multiple components, it's just one, but the sign, so positive or negative, tells us which direction that number is heading. And then the size of the number tells us how far away it is from the origin. In other words, what its magnitude is. So 3, for example, would be 3 units away from 0, and it's positive, which means we know its direction. -3 has the same magnitude, but it has a negative sign, which means we know the direction is the other way, right? So this is how vectors theoretically work. Now, in practice, we can kind of imagine them as these little arrows, okay? So it has a length, and it also tells us which direction this is facing, okay? But these directions and magnitudes can represent multiple different things, which you'll see when we discuss more about vectors, how this can be true. Now, we're going to take a look at this cube here, and I've got just one of the points for now, where we're representing its point position as this green vector, and the blue is the normals of that point. Okay. Now, I've got the grid switched on so that you can see that this point position is coming from the origin to that position. I felt that it was important to show you this because a lot of the time, imagining or visualizing point position like this, understanding that it is a position coming from the origin to its current location, is very important in sort of visually, artistically working with vectors and understanding how the vectors can maybe interact with one another. If we just imagine point positions as just literal locations floating in space and they have nothing relative to the origin, it becomes a lot harder to, in your head, just visualize how you can maybe add two vectors together or subtract them or do whatever. So I just wanted to draw this for you so that you could understand that all of these point positions, even if I switch on for the entire cube now, The entire box has all its points have a vector which is essentially saying from the origin which direction do I head and how long in order to reach my current location. Okay. Now with normals and normally usually Houdini will represent the normals like this with these little lines, but these are not accurate representations of the normal because they are not actually matching the same length. They have a multiplier. But really, the normal is normalized to a length of 1, which we will discuss more in detail later. So if you don't understand what that means right now, don't worry. But essentially what it means is this is 1 in length. Okay. And this cube is actually 1 by 1. And so you can see that this length here is very similar to the length. In fact, it's exactly the same as the length of this blue vector. So I decided to draw this for you to show that, this is a more accurate representation of what the normal actually looks like. It's 1 in length and it faces out along from the point outwards. But even that is not exactly accurate, and it's really important to understand. So I'm going to show you with normals how there's a slight misrepresentation of what they actually are doing. So let's pull up the geometry spreadsheet and we're going to have a look. Now the point that I've drawn to, the single point over here, is point 0. So this point that is highlighted over here, these are our point position values, so x, y, z, and our normal values, x, y, z. Okay, so let's look at the x-axis first, right? So that's here going left to right. This is x, right? And we can see that on the bottom over here. So we can kind of see this little gnomon that helps us see which direction. So this we're looking at is x. And along x, our point position is 1.6. So there's 1. And then there's 2, so you can kind of see that this is at this mark, which is 0.2, 0.3, 0.2, 0.4, 0.6. Okay, so exactly 1.6 along x. And it's 0.7 along y. This is a little harder to see because the grid doesn't extend up, but you can just trust me that that is at 0.7. And then it's negative 0.59. So essentially it's almost negative 0.6 along z, which you can see here. This is z, and you can see we're going into the negative. So these three numbers tell us the location of that point position relative to the origin. Okay, so always remember it or imagine it as a line going from the origin to that point's position. But the normal, now let's have a look at these values, right? So this normal has actually 3 of the same values, negative 5.7735 in both x, y, and z. Okay, but if it was sort of the same as this point position, sort of just relative to here where it's being drawn from, then this here we're in sort of like negative 1 point, maybe not quite, but almost negative 1.2. Okay. So why is our z value not negative 1.2? Because that's where this is. And then also along y, we can see that it's above the origin. Okay, it's above the grid line, which means it should have a positive y value. So why does it have a negative value instead? So the thing to understand with these normals is although they are drawn from the point position here, they are actually relative to the origin as well. Okay. Now, more accurately, they are relative to this point position, but relative to the matrix of this point position. So its own world where this point is the origin and the center of the universe. So that is more accurate to say, but when we add these two vectors together, it doesn't account for that, all right? It is transformed into world space. And so when we work with this vector and this vector, to represent them like this is slightly inaccurate. The more accurate way of representing it is like this, okay? So even though this is the normal for this point, it really is just a line from the origin in a certain direction and magnitude, which represents certain information that's attached to that point. Of course, it helps us to visualize it if we see it drawn from the point. Okay, and so that's why Houdini does it this way. When we switch on our normals, you see these normals at the actual point, because it wouldn't really be useful for us if they were all sitting at the origin. But from a mathematical standpoint, when we start working with these two vectors, we need to understand that this does not live here. It lives here at the origin. All vectors are relative from the origin to a certain location in space. Okay? And so now, when we want to work with these two, we're working with them like this. Okay? So this will make more sense later on when we start actually adding and subtracting vectors, but I just wanted to make sure, first of all, that you understood that point positions are not just random loose locations in space, but are actually vectors drawn from the origin to their position. And that normals and even velocities, anything that's drawn from the point, is really just represented from the point, but actually theoretically is from the origin as well. All the vectors you will see go from the origin outwards. Okay. Now this was just representing it on a single point, but if we show the whole box, this is really what we're looking at when we look at our X and Y positions in our geometry spreadsheet. So this negative 5.73, this is this one over here, right? Well, we'll go back to our point so you can see it. And this does make more sense along, let's just turn so it's a little easier to see. So here's our Z, sorry, this is X. So this is negatives and positives around the origin, and it is negative 0.5773, so almost 0.6, which is exactly where this is. And it's the same on Z, and it's the same on Y. And you'll see here on Y, it is below the origin grid line, and so we can see it's negative. So these are what is represented by what we're visually seeing here. And yet when we visualize normals in Houdini, it will tell us that they go from the point. Very important to understand this for us to move forward. Okay, so now we're going to work with these vectors and show you what it looks like to actually mathematically work with them. All right, so here we have an example that's going to show you how normal numbers basically are one-dimensional vectors. And the reason this is important to understand is because we can then use the same principles that we use for normal numbers, addition, multiplication, everything we learned in the first lesson, and apply them to vectors, because they really are actually the same thing. They just have multiple components the more, we go from 2-dimensional to 3-dimensional and so on, but they follow the same rules. And that's really the beauty of maths, is that it is just a bunch of rules, and when we understand them, it is very easy to kind of manipulate that sort of across a variety of different sort of methods and examples and applications for all of this. All right, so we're going to look at just a straight number line. Now, obviously, I've just had to sort of separate these into kind of layers over here so that we can see it. Theoretically, we're talking about everything being flattened on top of one another because it is one-dimensional. Okay, so there is no kind of y value to this. But what I've done just for the purposes of visualizing this is split them so we can see what our three different vectors are doing here. Okay. So just imagine them on top of one another, but obviously this becomes almost impossible to see. Right. So what we have here is a number line and then two vectors. Okay, so green and blue are the two vectors that we're talking about. And what we're going to be doing is adding these together. So it's same principles as what we learned in the first lesson about addition. And then we're also going to look at subtraction. So with same principle, but just using negation. But this is the fundamentals which we then apply to 2-dimensional, 3-dimensional, and then even 4- and 5-dimensional, or however many you need to go. you can apply these same principles. So something that's easy to visualize has then application for something that's almost impossible to imagine in our heads, like a 6-dimensional vector or something like that, right? So on this number line, we have our green vector, which is 3. Okay, and remember, it has direction and magnitude. So not only is it 3 in terms of magnitude, but its direction is positive. So it's headed in this direction, and it is 3 units long. Now, when we add our blue vector, which is 2 units long, we get the result of the purple vector here, which is 5 long. Okay, and it's obviously very easy to imagine this and kind of see it, where we have this plus that gives us that, right? But there's something that we're sort of doing here automatically because we understand how basic numbers work that needs to be pointed out, because if we understand why and what sort of shortcuts we're taking in our mind to add 3 plus 2, we can then apply that to our 2-dimensional and 3-dimensional vectors. So remember I said everything like with our normals in the previous example, our normals are drawn from the origin, not from the point themselves. Now this is kind of exactly the same thing. 2 does not start here. Okay, it starts at 0 and goes 2 units further, right? So this is actually what we're adding, is 3 plus 2, right? But in order to add it, what we need to do is position them from tail to head, okay? So that the head of the first vector is attached to the tail of the second, right? And because in addition, order doesn't matter, it really wouldn't matter if we put the green vector at the end of the blue or the other way around. And obviously, even if we had maybe 5 different numbers that we were adding together, you can arrange them and just literally attach them tail, head, all the way, okay? And the resultant vector goes from the start, the tail of the first vector, to the head of the second vector, all right? So in other words, it's literally just the sum total of those two, okay, which is basically just what addition is. But you see how this vector was actually here, and 3 plus 2 gives us 5. Now, it's hard visually to see how, we get a vector that results in this until we move them head to tail, and then we see that, oh, okay, I can kind of see that the entire sum of the length is that long, right? And it is the same for if we have negative values, right? So if we just have a value that is negative, for example, let's make be -1, we still apply it at sort of head to tail, okay? This is theoretically what it looks like. So we have -1 unit in length, and we're adding that to +3. So the result is 2. And if we position this vector as we should, so that its tail at the same position as the head of this one, then essentially we're moving along this vector and then back by 1, and so the result is 2. Okay, so this is how we add values. Even if they're negative, it's still the same rules apply. Now, keeping that in mind, let's switch to subtraction. So our operation that we're busy applying right now is addition. But what happens when we subtract? So we say A minus B, right? 3 minus 2. Okay, but it's not -2, it's 3 minus 2. Well, we go under the same operation that we spoke about before, which is negation. So you can see here there's the kind of grayed out blue, which is our original vector, which is +2. But we negate that vector. In other words, we reverse the direction of the vector. And that's something I want to point out with negate. Earlier when we spoke about it, it was simply reversing the sign. But the sign means the direction of the vector. On a simple number line, going positive to negative or negative to positive makes it reversed. but it also applies to 2-dimensional and 3-dimensional vectors, which with those it can be quite complicated because some of them could be a combination of positive and negative components. You could have positive x but negative y, and that's your vector. Now, if you want to reverse that completely, you have to negate all of the components. So we'll see how that works just now. Just in terms of this one-dimensional vector, it's as simple as flipping it around. So just reversing it to the other direction from that same point. So again, if we move this back to the origin, so this is actually what we're working with. So positive 3, and then plus a negated positive 2. So what happens when we negate positive 2? We get negative 2. And 3 plus negative 2 would give us 1. And although this is hard to kind of visualize, if we move it here so that the tail of the blue vector touches the head of the green one, then we're going 3 units this way and then 2 units back. So the result is 1 unit in the positive direction. Okay. And so if we maybe even flatten this a little bit, you can kind of see more. Obviously, like I say, they would be on top of one another, but when a little bit closer, you can kind of see that this plus that is that. And that is exactly what I meant by showing that negation is the way that we actually turn subtraction into addition. So we're adding negated values, but which values get negated is important. Okay, if we negated the 3 instead of the 2, we'd get a different result. Okay, so in this case, I'm negating my blue vector, but let me make my green one 2 and my blue one 3. Well, then we get a different result because our green is 2, but our blue is negative 3. Well, it's 3 actually, but we're negating it because we're subtracting it. So it gets reversed. We go 2 units along green, then 1, 2, 3 units back along blue, and so we end up with a value of negative 1, right? So negative being the direction of our purple vector means that it's headed in the negative direction instead of positive, and how many units? 1. So this vector has both direction and magnitude. Okay, so now let's take everything that we just learned about the most sort of simple way we can explain it and add one component. Let's add one dimension to this and look at our 2-dimensional vectors. Okay, and we're going to basically apply the exact same principles. So we're still looking at addition, but now we have 2 numbers for each vector instead of 1. Okay, and so ultimately here our number A, which is our green still, it is 3 units along x, so 1, 2, 3, and 5 units along y, 1, 2, 3, 4, 5. Okay, so there we have it. From the origin to that position, that is our green vector. Now, number B, which is our blue one, is 3 units and 1. Okay, 3 on x and 1 on y, 3 by 1. Now, you'll see this is also drawn from the origin. And if we had to say green plus blue, then purple here, this is the result, okay, which is 6 and 6. Now, we can see this in multiple ways. Let's look first just mathematically at the numbers. 3 plus 3, we know that to be 6. 5 plus 1, we know that to be 6. So if you just went and added up the actual individual components, you'll end up with 6 by 6, which is our result. So that's a way to do it just based on the numbers. But to understand physically and sort of visually what's happening, let's move our number B to the end of the green vector so that we can see what's happening. So same theory as what we applied up here, we move it so that the tail is attached to the head of the first one, okay, and we end up here. And that is then, so our purple vector goes from the tail of the first one, so which should always be at the origin, to the head of the last vector added. Okay, in this case, we're only adding 2 vectors, but let's say we added a whole bunch, like 5 different vectors. We just take the origin and we find the end of that chain of vectors, and that's the result of the sum of all those vectors. Okay, and then if we did this in reverse, so actually instead of moving that, let's say we left our blue one here and then we attached our green to here, well, the green vector would be going 3 along x. So from here, it would go 1, 2, 3, and then it would go 5 up. So 1, 2, 3, 4, 5. And so it would end up in the exact same position, right? So again, we can see how addition, the order does not matter. And visualizing it this way lets us kind of imagine what is happening. And remember our example of having the box? Well, if we had our point position, and if we add the normals, then what happens is it moves the point along the normals. So in other words, it just expands the size of that box, okay, which is essentially what's happening here, taking our position and offsetting it. Maybe a better example is if we imagine this blue vector to be our velocity. So this is a point in space, and then every frame we add its velocity. So adding vector 1 and vector 2, and the result is the new point position of the original point. So it moved from here to here. And on the next frame, if it is the same velocity, then this would be our new, our new number A. And this blue vector would simply be added. So we would go 3 units and then 1. And so we'd end up here. And so every frame, it's moving in that direction. So that's how something like velocity works. Now let's look at this with with some subtraction, right? Oh, and I just wanted to sort of show you like how this, as we move this around, it stays absolutely perfect. Yeah, I mean, even into the negative. Let's go here, some negative and positive values. Before we move on to subtraction, let's just look at a little bit more complex of an example where we maybe have number A is in the negative, but number B is actually all positive, okay? So essentially we're saying this plus that equals that. And it's very hard to visualize it this way, but as soon as we move them, so it's tail, head, and then purple goes from the origin or from the tail of the first to the head of the last in the chain, well, then we end up with that result. And then it's obviously easy to see it mathematically. You know, we can go 3 plus negative 1.7 and 1 plus negative 1.8. Okay, even if we had maybe a positive one there, but a negative. See, it doesn't really matter which direction we go. This all adds up to the same thing, right? Okay, so let's reset these two numbers that maybe are a little bit easier to work with, and then let's change to subtraction. Now again, the exact same thing happens with subtraction. We're saying number A minus B. So what that means is just addition, A plus B, but then it's the negated B. So first step, we negate B. We take the blue vector and we reverse it. We say, okay, you go there now instead of here. Just literally same direction. Well, you know, same direction line, but reversed. So it actually ends up in the opposite place, but it forms a straight parallel line, okay? Now, as I've said before, theoretically, this is what's happening, is we're saying, so if we say this number, the green, minus this over here, the gray blue, that minus that equals the purple. And that's very hard to kind of visually say. Like if I just had to show this to you, and we say, okay, ignore the purple, just look at the green and the blue, and say green minus blue. Very hard to sort of imagine what the result of that would be. But what we can do is visually imagine this vector, just reverse it, and then attach it to the head of this moving in. So we know because it's reversed, we're heading from here in this direction, 1 unit down, 3 units across, and so we end up at 4 along y and 0 along x, right? Which is exactly what we end up with if we subtract. Okay, and that's because we're moving that to here, but negating it, going from there in this direction and saying, well, we're now at 0 and 4. And then mathematically, we can see it as well. 3 minus 3 is 0, and then 5 minus 1 is 4. Okay, and so exact same thing happens. It's just like exactly the same as addition, but this number is just negated before the addition operation takes place. Okay. Right, so let's reset that. 3 and 5, and then we'll switch it back. Okay. So that's what we have there in 2 dimensions. And then our final example over here in terms of dimensions is, what if we project this now into 3-dimensional space? Okay, so we are not now just sort of flat as we were, but we now have a z component as well. Okay, well, as I'm sure you can imagine, all the exact same principles apply. And I just wanted to show you 1, 2, and 3 dimensions, but you can then understand that it applies to 4 dimensions and 5 dimensions and so on. Okay, not that we're really going to work with 5 dimensions, but you do still, you know, I mean, we work with 4, which is quaternions. You also have then matrices, which, you know, you can have 3 by 3 or 4 by 4. So we're talking about like 16 float vectors, right? But it all follows the exact same principles. So if I'm adding these 2 numbers, we're going 4 plus 1, 5 plus 1, 2 plus 6, okay? But really it's saying this green vector plus the blue vector. Well, in order to add it, let's put them tail to head, and the result is tail of the first, head of the second, okay? And then the exact same thing with subtraction. We simply negate one of the values, the value that is being subtracted gets negated, and so we end up with this. Okay, now I just want to point out, using 3D because it's one of the easier ones to sort of understand it and see what's happening, is subtraction is a very good way of getting from one vector to another. So let's say we have 2 points, our green point and our blue point. We want to make a velocity that goes from green to blue. How do we draw a line from green to blue? From the end here, we say, well, I want to go in that direction and that magnitude such that I will end up at the location of blue. Okay? Like kind of saying, okay, well, you're at your house and you want to go to your friend's house. Which direction do you go? Okay, you don't have to necessarily go all the way back to the origin and then retrace your steps. No, you can figure out how to get from your position to his position. Okay? Now, subtraction is the way to get from one vector to another. You'll see with addition, it's the purple result is not helping us get from here to here. If we added this purple now to the green, we'd get way far away from the blue. Okay, so this is not a useful vector to us in this case because we want to get from here to here. But it is useful if we subtract. In other words, we negate this value. Because if we say subtract that value, then what happens is we're essentially saying we negate it, and then we are attaching it there, and then this purple vector is formed. Now, it is kind of maybe going to be a little hard to see, but with our original purple vector, with our original green vector, if we added this purple one to it now, so this purple, in fact, yeah, maybe this angle will help you see that this purple vector is the result of how to get from this blue one to the green one. Okay, so the from is the one that we negate, and the to is the one that's left the same. So if we wanted to actually get from the green to the blue, then we would actually say blue minus green. We would negate our green vector, leave our blue the same, add them together, and that will give us the result of how to get from green to blue. And in this case, it's the other way around. We have negated blue, so what that tells us, the resulting purple vector is how to get from blue to green. And if you moved this here, you could see that it'll actually help you get in all directions. You can kind of see that it's going to help us get from here to there if we just follow that same direction. Okay. Right, now this is with addition and subtraction, and that's mostly what we're going to be doing with vectors, but sometimes we do want to add, multiply or divide them. It does get a little bit more complicated, but I want to just show you theoretically a way of understanding how, like visually, how these vectors are being multiplied or divided. And remember that division really is just inverse multiplication, okay? So we're going to use our two-dimensional vectors because they're a little easier to follow and understand than three, especially because I don't have to keep kind of rotating around. So it's going to be easier to just show you on 2 dimensions how we can multiply our vectors together, okay? You will not use this all the time, but if you ever do come across it where you're multiplying 2 vectors by one another, you can at least understand what the result is. Now these 2 grids over here that we're looking at are showing the same 2 vectors, okay? So that and that, that and that, right? Exactly the same. They're linked to these same numbers. So as I alter any of these, they are moving the same 2. But the purple is the difference. The purple here, this is addition, and the purple one on this side is multiplication, okay? But what is actually happening when we multiply? Well, really what it's doing is it's saying, okay, we have this green vector, and what we want to do is represent it on our grid. So the same thing, we have 3 units and 5 units, except that imagine that every unit on X was equivalent to the size of the blue one on X, okay? Now I know that's going to be a little bit hard to understand, but let me explain it by switching on this grid, right? So here we have a normal unit, so that's 1 by 1, right? So we know we have to go, for the green vector, we have to go 3 over and 5 up. Well, instead, what if we turned every single block into the same representation as our blue vector? Now, our blue vector currently is 3 by 1. So 3 on X, so every single unit of X for the green counts as 3 units instead, because our blue vector is 3. But then the height, so the Y value of our blue is 1. So now 1 equals 1. So what we do is we're essentially dividing this block into 3 by 1 because of the size of blue. And then we add up. How do we get to this green vector? So how many units over are we going? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're going 9 units along X, and then along Y, we're going 1, 2, 3, 4, 5, because there are no additional divisions here. Okay, so it's 5 up and 9 across. Where is this purple vector? If we switch off this grid, where is it? It's 9 across and 5 up. Okay, now let's maybe just do one more of those where we do have some X as well. So let's maybe take, in fact, yeah, let's do something interesting like 1.5. Okay, so what we're doing is we're actually dividing up the single block into 3 units, because remember our blue is 3 by 1.5. So we divided 3 along X, but along Y it's actually equivalent to 1.5 units. And then in the next block it's the other half and then 1. And then the next block is 1.5, and then this one is half and 1, and so on. So now we count our green vector again. We go across. So how many do we go across? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 across, but along Y, we're going up by 1, 2, 3, 4, 5, 6, 7.5. Okay? And so let's have a look when we switch off this grid. Where is our purple vector? 9 across and up along Y, it's 7.5. Okay, so really a way of understanding it visually is that what we're doing is we're just counting what the green vector would look like if every unit of the grid was equal to the size of the blue. Okay. And it does work the opposite way as well. If instead we divided the grid into the size of the blue, of the green, and then counted where our blue vector takes us, that would be the same result on purple because, as we've said before, multiplication, the order doesn't matter. Now, I haven't put together a division example here because if multiplying vectors is not super common in 3D, dividing them is even less common. Very occasionally you'll come across it, but it's easy enough to understand that basically it's exactly like what we said before. It's the inverse vector. So if we're going to say green divided by blue, all you're doing is you're saying green multiplied by the inverted version of blue. So it would just be 1 divided by blue. Okay? And so that's sort of a way of understanding how multiplication with vectors works. But as I say, you won't really use it that often. Mostly addition and subtraction is going to get you primarily most of the way. And when we do multiply vectors, normally we're multiplying it by something like a matrix, which is in itself a 16 or sort of 9 float vector, depending on whether it's a 3x3 or a 4x4 matrix. But that's very hard to visually sort of represent in terms of a vector because you can't really draw like a 16 float vector. So when we're multiplying, we're normally just multiplying by a matrix. And we will talk about those a little bit later just so that we can visually understand what that's doing. But here, if you're ever wanting to kind of understand what's happening when you multiply two vectors, this should at least help. All right, so next we're going to look at how we can basically use this vector maths that we've learned up till now in 3D in sort of a practical way. So I have a basic scene here set up. We have a cube at the origin, right? So there we are. And I'm in X-ray mode just because we're going to be looking at these vectors, so it'll be easier to see. But anyway, we have this box that's created at the origin. We are creating normals on it. So we have a facet, which we will be using these normals a little bit later. So that's what the normals look like. And then we have a point VOP where we are doing some maths, right? And I like to think of VOPs essentially as maths nodes in Houdini. You know, a lot of the other nodes, they have particular function, but a point VOP really is just maths because you've got incoming attributes and outgoing attributes, and everything that you do in the middle essentially is all maths. So what we're doing inside of this point VOP is resulting in the cube moving positions, okay? So let's take a look at what's happening inside there to figure out what's going on. Okay. So I've got a few things, but really what's actually happening is just one simple addition. We're going to go through all of these just now as different examples to show how our maths can be applied. So what I'm doing is I have my point position here. So this is literally just the vector, which, as we've discussed before, if I switch on the green vectors here, this is what my point positions actually look like. They go from the origin, which, because this box is centered at the origin, means that from the center of the box is actually the center point of the entire world. And then each point, each of the 8 points, has a vector that goes from the origin to its position. Okay, so this green vector is basically what's here. What's coming out of this, P over here, point position, is the green vector. Now, I have a constant node over here. So this lets us feed just one single value, and it can be, any different type that we choose. In this case, I've chosen a vector. So I've created a vector, a constant vector, where I'm giving 3 different values, but this is the same value for all of the points. Now, I really want to point this out because this is a fundamental for understanding the maths and how Houdini works, and also how VOPs work. So this is going to help a lot of people across the board, is to understand and distinguish between different information per point versus single constant value. So for example, point position. Point position is not the same on all of these points. This point has a different position to this one. This one has a different position to that, and so on. They all have different point positions. So the value that's coming out of here is not one value, but an array of values where each point has its own unique value. But then what I have here is a constant. This means that this value is the same no matter which one of these points we're busy adding it to. Okay? And this one is our blue vector. Okay? So you'll see here now, in fact, I'll switch the grid off just so we can see a little more clearly. You can see what's happening here where the blue vector is going from the origin to this position in space. Okay. And that's what's resulting in the offset that is happening of the entire cube. But you'll see that the cube is moving, the entire cube and all of its points are moving because we're giving it one single constant value. And that means that each point is having that same value added to itself, but because it's starting in a different position, then this green vector plus that blue vector would result in a different purple vector than any of the others. So if I switch on purple, you'll see this is the result of saying green plus blue is purple, which is the convention we've stuck to so far. So you guys should be used to this by now. The green plus the blue is the purple. So we've got different green values, one blue value, and then different purple values. And because they're all these green ones are getting the same blue added to it, they end up in the same position. Right, so let's examine that. So let's take one point at a time. Okay, so we've got this one blue value, but let's take this point, for example. The green vector is showing its position. We want to add the blue. Well, when we add it, we want to move that blue to the end. In other words, the tail of the blue attached to the head of the green. And then we look at where the result is. And the result goes from the origin to that point, and that it will be our purple vector. Okay, so let's move the blue. Now, what you'll see that happens here, when I do move it, I'm actually splitting it up because each of these points, although they have the same blue vector added to them, because we want to arrange the blue where it goes from the tip of the green, we need to kind of go, okay, well, I'm going to place the blue on the tip of this green one. But also, if I take that same blue vector and put it here and the same blue vector and put it there, then we're going to result in each of the points being offset in that same direction by the same amount. And so that's what results in this kind of uniform offset where, you know, the points are moving, but it doesn't look like they're deforming because they've all moved by the same amount. And so here you can see now, I don't know, it's a little difficult to see, but basically the green plus the blue equals the purple. Okay, so it forms a triangle, right? And it's the same for each point. So we end up with new positions for the green. So this purple would be the new green. They were here. Now they're this. These would be the new point positions. These are the old point positions. And the reason they've changed is because of that. But that is actually one single value at the center. Okay. So that shows how we add a constant value. Now it is different when we add a value that is unique per point. Okay. So remember we created our normals here. Well, let's go back to using those. So our normals, which point outward, okay, and remember they do actually live at the origin, but for the sake of visualization, it's easier to sort of draw them from the point, so you know sort of which direction they're headed from that point. So what we're going to do is take our original vector over here, so our original box like this, and we're going to add the vectors, so the normals to the point position. This box is unaltered, but if we add normals to it, because the normals are unique, same as the point positions, each point has its own unique position and it also has its own unique normal. For example, this point has this normal that's facing this way. None of the other normals face that same direction. So we're taking point position, which is unique per point, and normals that are unique per point. But in VOPS, when we add them, because it runs over our points one at a time, it takes the matching point position and normals. So in other words, the point position for this point and the normals for that same point. And it adds them together and gives us a result. Okay, so that's what I have over here. I'm just passing through a null just so it's easier to sort of see. But what I'm doing here, so you see, we've essentially peaked this cube. So we've essentially grown the cube along the normals, okay, which results in a larger cube. So it's been expanded by the length of the normals and in that same normal direction. Okay, so let's look at what's happening with these vectors again. Now the green we've seen before, that is unchanged because the green is our original point position. But now the blue, instead of being one static value, the blue that we're adding are our normals. Now the normals go from the origin to 1 unit away, but actually we're going to just blend them. So we're going to move it so that the tip of the blue, so the tail of the blue touches the tip or the end of the green. Okay, and then the result is going to go from the tail of the green to the root, or sorry, tail of the green to the tip of the blue, and that's going to be our purple. Now it is a little hard to see because they are the point position and the normals are exactly on like in a line with one another. But if I switch off my blue and green, you'll see what the resulting purple vectors are, and those are our new point positions because we've essentially moved them along the normals. So if you take point position plus normals, then you get a peak. Okay, so you get peaked vectors, right? And then let's move to another example. So we've given it a constant value, but what if we have a random value? Okay, but it's a random value that has no additional seed built into it. Okay, now how random numbers work, especially in Houdini, but across most of sort of mathematics and computer programming, right, is when you have a random number, it's not actually really random. It's not truly random. It takes what's called a seed, right? And so it's kind of a random number, but relative to that input number called a seed. So random of a number 1 will give us a certain random number. Let's say random of seed 1 is 0.5, okay? Then if I do it on my computer and plug in a seed of 1, and then the result will be 0.5, if you do it on your computer, it will be exactly the same. It is not completely generating a random number like rolling the dice. It's based on the number that you feed it. So then we change the seed to maybe 2, and maybe the random for 2 is 0.1. Okay, so you see it is kind of random, like there's these just disparate numbers that are attached to the seed. And so it results in what kind of looks or appears to be random, but really if we changed our seed back to 1, it wouldn't now be a brand new number. It's not rolling a random die every time. If we changed it back to 1, we'd get back to 0.5 as a random number. Okay, so that's how randomness works in Houdini. And so if we do not feed it an additional random per point kind of seed value, then it's only looking at the seed that we give it here. Okay, in this case on random they call it position, right? But it is essentially the seed. Now, so we give it a value 6 here. It's going to result in a random vector, and it's going to be the same random vector for all points. The reason for that is because I'm not doing anything different for every point. So you know, these are unique numbers per point. But because we're not plugging anything in here, it doesn't matter whether we're on 0.0, 0.1, 0.2, the number that comes out of here will be the same. So it's almost exactly like what we did here with our constant, except the constant, I'm choosing the numbers. With a random, I'm not choosing it. I'm only choosing the random seed as an input. So if I place that there, you'll see that our cube has moved again. Now it has moved to a different position to our constant, but it still has maintained the exact cube shape, and that's because it's moving. You'll see our blue are all identical. In other words, if I move it to the center, you can see when they overlap that it is literally just picking the same vector no matter which point. And so every point has that vector added to it, and so that it gets to its new position, right? And if I change the seed here, I get a different random vector, but it is still the same random vector for every single point, okay? Which means that it's gonna essentially maintain the relative shape and size of this box. Now, instead of feeding it a random constant value, so a constant seed for the random, if we do feed it something that is unique for every point, for example, maybe we feed it the point number as the seed, then each point has its own number. So point 0 is actually going to result in this random vector that we're looking at right now. So 0 will equal this, but 1 will equal that, and 2 will equal this one. And so because each point number is unique, it's going to add up to a whole collection of random vectors, one per point. So if I plug it in, you can now see all of those vectors are different for every point. So every point now has its own point position, but it also has a random vector. And when we add those two vectors together, it results in a random position for every point. And that's why the cube gets deformed. Okay, it used to be just a normal cube, and now it's this weird kind of strange arty shape. Okay, so let's just have a look at what's happening with the vectors here. Our green vectors, our original point position, still exactly the same. Our blue vectors, these are totally random per point based on the point number. And so when we place these at the end of the green vectors and add them together, the result going from the origin to the tip of the last vector will be our purple. And so the purple is our new point position, which is where it moves each point to. And so this is why we get this result. Okay. So this is kind of an example to show you how adding different vectors can give you different results. You can peak, so like that, peak along the normals, or maybe peak move your positions along velocity. You can offset it by feeding it a constant value. You can give it a random constant value, which will move all the points the same way, or random values per point, and then that will give a sort of a noised value. Okay. Now, one thing I want to show you over here is averaging. Now, we're going to talk a little bit more later about averaging, but for now, I just want to show you a visual example of it so that it will help explain. So let's say we take our random position here. Okay. So we've got our random position added on to our point position, which results in our new position. Okay. Now remember, our random value is not the purple. That's the result. That's what's coming out of here. This is the purple value. But this is green at the top. This is the green. And this at the bottom is the blue. And we're adding them together, which gives us the purple value. Okay. So the blue one is what's here. And if we add that with our green, as opposed to if we take both those same two vectors and average them. Okay. So you'll see here my position and my average have the same two inputs. Then when I put this as the result of my position, look at the different result that I get. Okay. Now this result is essentially looking at the, well, let's do it this way. It's essentially looking at the original position, which is the green one, and it's looking at the blue values, which were totally random. Okay, remember here, these are our random blue values, and it's taking kind of a halfway point between these two vectors. So if we had to put them here, and it's looking at this vector, the green one, and its associated blue one, and finding a point that is actually halfway between them, right? And that's what averaging is doing. So you'll see here that the average looks similar to what the cube what the random kind of weird shape looked like. But it's a scaled down version because it's blended closer towards the original cube value. Okay. Now, mathematically, what is happening in an average, okay, is if we took our addition, so our added value instead of our average, right, so this result, and if we divided by 2, then what we would get is the exact same. So let me just rearrange the notes here so it's a little easier to see. So, in fact, that'll be easier. Okay. The average amount looks exactly the same as if I add the 2 vectors together and then divide by 2. So there's nothing changes between these two. As you can see, as I switch, nothing changes. And the reason for this is because that's actually what averaging is doing. It's adding up all of the vectors, so it's taking the sum of all of it, but then it's dividing by the total number of inputs. So that's where I'm getting 2 from. Okay, you might think like why 2 specifically, but it's not always 2. It could be 3 if we feed it 3 vectors. So let's add our constant vector in as well. So not only do we have a random per point, we also have a constant. Now what it does is it adds them all together. So this is the result, okay? So it's moving it away from the origin and adding some random values, okay? But then because we're adding 3 values together, if we divide this by 3, so the number of vectors that we're looking at, then the result will be the same as if we averaged all 3 of those vectors. So these are the same 3 vectors, and if I average them, you'll see there as I switch, nothing changes. Okay, so, and when we're talking about average, and we're going to talk about it a little bit more later so that you understand in more detail, but average is calculating the mean average, okay? And so this is the same, the method of taking the sum divided by the number of values. Okay, so we've got 3 incoming values, add them together, divide by 3. Gives us the same as the average. And it works for vectors as well as it does for numbers or arrays of numbers or whatever it is. Okay. All right, so there we go. That's one example of how the sort of addition and subtraction can help us. And now we're going to look at another one. Okay, so we've looked at how adding vectors can be useful for manipulating points and creating different shapes or offsetting particles or point positions. But this is an example that we're now going to look at for how subtraction can be used extremely usefully in 3D, especially when it comes to vectors. So in the scene, I have a box and I have some normals on that box. Right, and then I also am actually calculating. I've got a very large sphere over here that I'm sort of scattering some points on, just to get some random floating points in space. In fact, let me switch that off for a second. So I've got these sort of random points and my box, and what I'm doing is I'm raying. Okay, so I'm using the raycast node. If you haven't used this before, it's essentially just finding its position on the surface, the nearest surface, right? You can feed it either an actual vector, or in this case, I'm just asking it to find the minimum distance. So in other words, the shortest point from where they currently are to the position on the surface, okay? So here, if I switch on my point numbers, you can see the difference between the point versus where it wants to be, its nearest position on the surface. Same as with this one over here, it has a little point on the surface over there where it is the nearest position. Okay, and what I'm doing in this point VOP is I'm comparing those 2 positions. In one scenario, I'm adding them, and another I'm subtracting them. And that's what I'm going to be showing you here, is switching between addition and subtraction to show you the different results that we get, and why we use subtraction to then calculate essentially delta. So it's like the difference between one vector and another. Okay. And I'm feeding these particles into just a very, very simple pop simulation, which has the original box as a collider, and it has that vector that we're creating in here through either addition or subtraction as the velocity, so the point velocity, which means these particles are going to move in the direction of the vector that we feed it. Okay? And then we'll see what happens. Because ultimately we can use this ray, so the difference between its rayed location, which is a vector, and its actual position, which is also a vector, to then set what we want to happen with the velocity and where these particles should move. Okay, so let's examine our vectors in order to do this properly. So if I switch on green as we've become accustomed to is the position of our points. Okay, so I'm using green to represent the actual point position for each of our particles. Blue is the position on the box, so the rayed position. In other words, it is this position here after being rayed onto the surface. Okay, now the ray does move the particles to the surface, but I'm not wanting to do that. I'm just simply using that as a vector to then interact with here. So I'm keeping my original point position, so I'm keeping the green, but I'm adding in the blue as an additional vector, and then we're using these two to calculate the purple vector. Okay, so let's have a look at what this results in. So if we add these two vectors, so we've got our operation set to addition, then I'm sure you guys know what to expect by now. We've done this enough times. So green plus the blue, right? So we would move the blue to the end, and then the result would be from the root to the tip. So this purple vector would be what our resultant velocity would be. Okay, and the length of it obviously is the speed, so how much velocity it actually has. And then obviously the direction is important as well. So instead of, just basically remember that although we move the blue to the end, okay, it is obviously just, these two vectors being added, okay? But if I switch off blue here, now this purple is the result, and green is still our point position. We're going to be setting purple as the velocity of these points. And velocity, again, very similar to normals, like we have seen before, where it's easier and more visually accurate, sort of more visually understandable to represent it at the point of the actual point's location. But theoretically, it really lives at the origin. Well, that's kind of the same thing that's happening with the purple vector now. This purple vector is sitting at the origin, but if it's used as velocity, what's really going to happen is that it adds that vector to the point position on every frame. Okay, so that's what happens with velocity. Essentially, it's just adding to point position, but multiplied by the time step. Okay, so that purple vector is where our positions should essentially be moved along. Okay. And if we click play, you'll see what happens there. You can see these particles flying along here. In fact, what I may do is quickly just increase the size of my particles a little bit so that we can more easily see them moving. Okay, so they start at the green vector, but because we're adding the blue, what that results in is the purple. But because the purple should be relative to the current position of them, if we move the purple there, then we're saying what's actually going to happen is the green plus this purple is going to result in it moving along these lines, and it's going to continue. It'll just keep going out. Okay, unless we drag or change the velocity in some sort of way, it's just going to keep going. All right. Now this is not what we wanted. What we wanted ultimately was to get it to go toward the box. I mean, maybe if you do want it to move away from the box, and this is a perfect way of doing it. But we want to say, I want you to get towards the box. So we're using the ray to determine the location we want it to end up in, but we also want to get there not instantly like the ray does, but we want to simulate it. We want to see frame after frame how our particles move towards and eventually collide with our box, okay, at these exact locations. So if we go back and show our blue and our green vectors, instead, if what we do is we subtract, because remember what I said to you before, to get from one vector to another, subtraction is how we calculate that difference. And in fact, you'll often hear the word difference in the same sort of use as minus or subtraction. You talk about the difference between something. That means you subtract one from another. Okay? But remember, with subtraction, the order matters. Now, really what we're doing is we're adding a negated value, but which value we negate matters. And the one that we negate is the one that we go from. So what do we want to do here? We want to go from our green towards the blue. So we want the purple to go from here to here. And in order to do that, we need to negate our green and then add them together. In other words, subtract. But what it is blue minus green. If we went green minus blue, that means green plus the negated blue. And that would mean we would go from blue to green, okay? Which would then result in the particles moving away from the surface. Not along the current point position as we already had in the previous example with addition. So not out this way, but actually out away from the surface directly, as in like almost in a tangent from the surface. It would move directly away, okay? If we subtracted blue from green, but we're going to do it the other way around because we know we want to go from here toward the blue, okay? So let's switch to subtraction. So in all that's happening is that when I switch here, is that in here I'm switching this switch. Okay, so we're actually just subtracting instead of adding, but it's the exact same two. Okay, so here's what happens. So now we've got the same two vectors, but because we're subtracting, what we're really doing is we're switching the green. We're negating the green vector. And then we're making sure that the blue and the green are positioned in such a way that it goes from the tail of one to the head. So then the tail of the next one touches the head of that one and then goes. So this is exactly perfect. Okay. It goes tail of green to the tip of green, tail of blue to the tip of blue, arranged like that. Okay. So we don't want to shift it like this, where it's tail to tail. Instead, it's tail to tip. And then the purple result is going to go from the tail of the first to the head of the other. Okay, so like that. That's exactly the vector we want. If we negated the blue, we'd have actually the same vector, but just with the opposite direction. So it would be reversed. Okay, so negated. And so this is going to be our velocity that we add to our points. Now, the green is only negated in the calculation of the purple, so we can actually switch it back and say, okay, well, this is still the actual position of the points, and we can switch off the blue. We have our point position, and each one has this purple vector, which is the velocity of those points. And that velocity is now pointing toward the ray point, okay, the ray position. And since that's set as velocity, if we now hit play, you'll see those particles move exactly along the direction that we wanted them to, and then when they collide with the box, they turn red. Okay, so let me switch off the purple vector and even the green one just to show you what's actually happening here. We have these particles moving directly towards the surface, which is exactly what we wanted them to do. Okay, so that's exactly what's happening there, and that's because of subtraction, essentially this sum. Now don't forget that this purple vector actually means this, okay, because all the vectors always go from the origin. But when we calculate it in this way. We visualize it so that it goes tail, tip, and then the result goes tail to tail, tip to tip, and that's the result. But that result is actually a vector that looks like that. But because it's added to our original position, because it's velocity, it results in it moving in that direction. Okay. Now, if we had subtracted them the other way round, so in other words, if I come in here to my 2 points and I swap the subtraction, so the position, which is green, so green minus blue instead of the other way around, then you'll see that the result will actually be very different. It's going to move in the opposite direction. Okay, so you see our purple is what we wanted, but instead it's going to move in the opposite direction. Same direction, sort of. So in other words, the same line, the same plane, but the wrong way. And if you get that result, which often does happen because sometimes it's a little confusing when you're working with these vectors, then you just swap the actual order of the subtraction, and then you'll get the right direction. Okay, and that just shows now how subtraction can help us calculate the difference between vectors. Because what we really started with was one point over here, and we said we want these points to touch the cube. We literally want to have them kind of move towards the cube and collide with them. So we raid to calculate the blue vector, subtract green from blue in order to get the purple, and set that as the velocity of the particles so that they move in that direction. Okay. Right, so now that we've kind of handled the basics of vector maths, addition and subtraction, multiplication, and kind of how to work that in a practical way, we're going to move on to some more kind of advanced mathematical formulas, but that rely on vector maths. So we're kind of going to do like a part 2 of how to use vectors to do some amazing things.